Now that we know something about inverse functions, let's take a look at the graph of both the exponential function and the logarithm function. Let's start here by constructing the graph of y equals 2 to the x. I'm going to do this by creating a little table. We don't have to go very far. And we know basically what it looks like, right? The base is bigger than 1. We've got 2 to the x. So this is the basic form, bigger than 1. So this is a growth function, so we know it's going to look like this, right? We know it's going to come through and look like this. Let's see if we can get a little bit more accurate, though. So suppose x is 0, and what we get is 2 to the 0, which is 1. Let's plot that point. So 2 to the 0 is 1. Now that's going to be way down here, pretty tight. All right, and then suppose x is 1. We'll get 2 to the 1, which is 2. We'll plot that point. So over 1, up 2. Now let's suppose x is 2. We'll get 2 to the 2, which is 4. We'll plot that point. So over 2 up 4 brings us here. Let's go to 3. At 3, we get 2 to the 3, which is 8. All right, we'll plot that one. So over to 3 up to 8, I think is right here. Let's try a few more. How about 4? When x is 4, we'll get y is 2 to the 4, which is 16. So we'll come over to 4, right? So I'm at the origin down here. I come over to 4, and then all the way up to 16. So we'll put a point there. I think we can probably do one more. How about if we use x is 5, we'll get 2 to the 5th, which is 32, and that will put us, all right, here's the origin, over 5, all the way up to 32, way up there. Now, if we went to x equals 6, we'd be out at 2 to the 6 is 64. We'd be way off the graph. But we got enough to give us an idea of what's happening with it now. So as best I can, I'm going to draw a curve through these points here. I know it looks like this. Okay, I'll try to draw in a smooth curve. Come on. All right, that's kind of what it looks like. Y equals 2 to the x. Now, I'm going to use decimals and get a really good graph of this. Now, I took out the graph that I generated by hand, which was a little bit shaky, and I put in this new graph that I generated using the graphing software Desmos. And I labeled the points so you can see what we have here. Here is 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, 5, 30, 5, 32. Now this is the graph of y equals 2 to the x. And you can see because it's, when you come down here and start at the left, all right, start at the very left, and as you move, you're always moving to the right. You never come back on itself like this. You're always moving in one direction to the right. That means that this is not only a function, but it is a one-to-one function. And because it is a one-to-one function, that tells us that the inverse exists. The inverse function exists. So what we want to do, of course, is to graph it. Let's see what the inverse function looks like. So let's construct the graph of y equals 2 to the x, which we just did, and we'll use that graph to generate the graph of the inverse. So let me put a coordinate system in here. So I popped in a coordinate system with the graph of y equals 2 to the x. Right there it is, y equals 2 to the x. That's the one we just generated. And now I want to get the graph of the inverse of this function. Now I know I can get some points that lie on the graph of the inverse function if I just switch the order of those components. Right? 0 goes to 1, so the inverse 1 goes to 2 up here. 3 goes to 8, and the inverse 8 goes to 3. So let's just plot these points here, but with the components reversed. So first up, let's take this point here, 0, 1, reverse those, and we'll go 1, 0. So let's plot that point, 1, 0. It's going to be right here. Now let's do this one. This is 1 goes to 2, so 2 will go to 1. So let's go over 2, up 1. The next one, 2 goes to 4. So reverse them, 4 goes to 2. So over 4, up 2, puts us here. And then the next one is 3 goes to 8, so 8 goes to 3. So down here, 8 over 8, up 3, puts us right there. And then the next one is this one way up here, right, 4, 16. So now we've got to go all the way out to 16 just to get up to 4. So start at the origin, all the way out to 16 just to get up one more unit to 4. And then finally that last one at the very top that we've got, 5 goes to 32. So 32 goes to 5. So that's going to be way out here. So we've got to go all the way over to 32 just to go up from 4 to 5. All right, so let's see. 32 and 5 looks like here. And then if I pass this curve through here, I'm going to do this with Desmos in just a minute, but you can see it kind of looks like this. Now how did I know what to do here? Well, this curve right here is always above the x-axis, so when I take any point here, it's always going to, the y-coordinate will always be positive. So when I switch it, the x will always be positive. Now I'm going to take this curve out and put in the curve generated by Desmos so it looks a little bit better. These three curves on this coordinate system I graphed using a graphing utility called Desmos. It's free. Just go to Desmos and you'll find it. So up here, this is the one that we generated here. This is y equals 2 to the x, right? So this is y equals 2 to the x. Then what we did is we just interchanged all of these points, 4 to 16, 16 to 4, and we got this curve right here. Now this is the inverse of 2 to the x. Now we're going to give this a name, and we call this function here, right, y equals, now this is the log base 2 of x. So we know that the exponential function is 1 to 1, so it has an inverse, and that inverse is going to be the logarithm function. Now the base here is 2, so we call this inverse function the log base 2 of x. If we had this 3 to the x, this down here would be log base 3. Now notice some interesting features about this. Here's this line, y equals x, right, that 45-degree line, and sure enough, do you see this? If you were to take this e to the x curve, right, take this one here, revolve it about this line, I'll show you what I mean. Right, if you take this whole thing and just flip it over about this line here, right, if you just take the whole thing and flip it over, one curve is a mirror image of the other. And that's a standard feature with inverse functions. Now here's some important features of the log function. Right, the domain of the log function, now to any base, no matter what base you use, this one just happens to be base 2. But they all look like this, right? All these curves look like this. Some of them bend a little bit more, a little bit less. But the domain, what can you put numbers in for x? That's the domain. Well, the numbers that you can put in for x has to be greater than 0. So the domain, I already wrote that, the domain is this. X has to be strictly greater than 0. You could try it on your calculator. You can try putting in log of 0 or the log of some negative number, and you get an error. The only numbers that you can take the logarithms of are positive numbers, right? And that you can see it kind of on the graph, although it's pretty tight in here. But the domain is no zeros, no negative numbers, but only positive numbers. The range, well, the range, that goes from negative infinity to infinity. Like the range, these are the y values, the output values. This curve keeps going down toward negative infinity, and this very slowly rises up to positive infinity. Now also look at this. If you take numbers and your domain, if you take x values, your inputs, less than 1, right? So if you're less than 1, you're kind of in here in that little range right there. What are the outputs? The outputs are negative, right? So if we say this, for 0 less than or equal to x, strictly less than 1, what do you know? The log of x is negative, right? So you get negative numbers, negative outputs. Put in an input value between 0 and 1, strictly between 0 and 1, and the output's going to be a negative number. And if you put an input value bigger than 1, right, not less than 1, not equal to 1, but bigger than 1, you get a positive number, right? So for x bigger than 1, the log is positive. So you choose a value, a small one, like between 0 and 1, the output is negative. You go bigger than 1, and the output is positive. And then, no matter what base you use, the logarithm, any base of 1, is 0. Right, so the log of 1 is 0. Right, there it is, right there. There's a picture. The log of 1 is 0, and it doesn't matter what base. This picture shows the base 2. But any base you use, the log of 1 is going to be 0. Now these two functions, 2 to the x and log base 2 of x, these are inverses of each other, which means one of them undoes the effect of the other. Suppose I started here. I start with x equals 10. Suppose I put in a 10, and I'm going to put that 10 into this function right here. I'm going to put that into f. All right, so I'll put that into f. And then what I'll do, right, I will put that into f inverse. So I'm going to start with 10. I process it with f, and then I undo it with f inverse, so they will undo each other. So I should be back at 10. Let's just verify that. So let's just write straight down f inverse. Now what is f of 10? Well, f of 10 is going to be what? Put the 10 into f. Now here's f. Put the 10 right here, so you get 2 to the 10. Now, what do you do with the 2 to the 10? Well, you put that into f inverse. So I'll put that 2 to the 10 right in here. So now I'm at log base 2 of 2 to the 10. So what is this? Well, you know that this is an exponent, right? Logarithms are exponents. So logarithms are exponents, so you know you're looking at an exponent here. And exponents go on bases. So the base here is 2. So if I take that 2, I got to think, what exponent would I put on that 2 to get this thing right here? Well, it's pretty obvious, isn't it? You're going to put in a 10. So the idea here is that when the bases match, these functions, the exponential and the logarithmic function, undo each other, and you just get what you put in. You just get your input. You know, if this seems a little bit peculiar, think about it like this. What if you start with a number 5, and then you do a multiplication and a division, something that we're used to. So you multiply it by 3, right? And then what do? Right, that gives you 15. And then what you do is you divide it by 3. So where are you? You're back at 5. All right, so you start with some number, you multiply it, then you undo the multiplication with the division, you're back where you started. Now that's the same thing here. I'm starting with 10, I exponentiate it, and then I undo the exponentiation using the log function. Just like multiplication and division are undo functions, just like they undo each other, just like addition, subtraction undo each other. Now what you have is exponential and log undoing each other. Of course, these undo each other only if you use the same multiplier and divisor. These undo each other as long as you add or subtract the same number. These undo each other as long as you use the same base. So a general statement here is this. I'm going to write it kind of backwards. If I start with some number x, and then I exponentiate it. Now over here I used 2, but I don't have to use 2. Just use any base, bigger than 0, not equal to 1. So this is called, I'm exponentiating the x. This is an exponential. So I start with some number x, I exponentiate it, but then I undo it by taking the logarithm base b of this thing. So what do you get? You're right back at x, because b, the exponential, is undone by the log. But I could also think about it the other way. If I start with x, take the log base b of x, and then exponentiate that by raising it. When I exponentiate something, I'm using it as a power. So I take b to that power. Where am I? I'm right back to x. So in both of these cases here, I've got an exponential and a log, right? An exponential and a log, and the bases are the same. So as long as the bases are the same, I'm just going to get that input value.